start by showing my face.
Hi. Yep. Hi, everyone. This is Dr. Alex Klein-Paste, who will be presenting the third webinar in the CESTiCC webinar series, Sustainable Winter Road Maintenance Operations. He has requested that questions can be asked at any point during the time. So if everyone can please keep their microphone muted when they do not have a question to ask, that would be appreciated. And with that, I will turn it over to Dr. Alex Klein-Paste for his presentation.
Thank you very much, Vicky, and welcome everybody. And thank you for coming and listening to this presentation. I will stop my webcam so you don't need to see my face 45 minutes. That will be rather boring. So yes, I'm then working normally as a professor at the Norwegian University of Science and Technology, where I'm leading the Norwegian Winter Maintenance Research Center. So that's my background. And today I'm going to talk about the fundamentals of plowing, anti-icing, de-icing, and sanding. So a little bit, I will start this talk by talking a little bit why I wanted to make this talk or this chapter in the book, before giving a short introduction and starting in some definitions, and then we dive into these fundamentals of both plowing, anti-icing, anti-compaction. I will explain what that is, and then de-icing, sanding, and we sum up everything by a little knowledge map. As Vicky said, please just ask a question whenever you feel to that. I will try to answer it either directly or I will just come back later to it. Why this talk? In my experience, I feel that quite some newcomers who have a need or desire to get some of the basics presented in an understandable way. Every year in Norway, at least, there come new people in the sector, and it is not so easy to understand all the words and all the terms and all the things people are talking about. So maybe this could be valuable for them. For those of you who are working at universities, there used to be a bunch of students who are very eager and may want to dive into this topic. And for them, it's always nice to have a kind of standard reference where they can refer to if they want to tell something about the basics or want to refer to that. And hopefully, maybe, possibly, there is also some values for more experienced professionals. And the reason is that if you talk about real winter maintenance, it's really dependent on the competence of the people who are doing the job. The guys and the women who are behind the steering wheel, and they make a lot of decisions, either when they're there or before. And this is kind of a philosophy of me. If you combine experience with some theoretical background, you will gain much more competence. So hopefully this can give some kind of structure of knowledge for them, which they can use to understand their daily life. So why do we do winter maintenance? Well, it's rather obvious that we do that to try to prevent these situations I illustrated here. Obviously, we don't want too much slippery surfaces, which basically is a problem caused by too little tire pavement friction. We don't want too much rolling resistance either. In this case, this elderly woman, she chose to leave the sidewalk because it was too much rolling resistance and rather walk in an area which is more dangerous for her and it's not designed for her to be there. And obviously also in a big scale, large rolling resistance can give problems in slippery slopes and can cause mobility problems. And the last issue is related to rutting and evenness, which can cause severe damage to vehicles, suspensions, steering bars, stuff like that, and simply just driving comfort. So to do all that, we do something. We do what we call winter maintenance or winter operations. And in this talk, I just define it, or I prefer to use this definition, which means it's all human efforts to monitor, control, or improve the pavement surface conditions. And when I talk about pavement, I'm referring to the American English meaning of pavement, meaning any paved surface. The British people would understand this mainly as the sidewalk, but for me in this talk, I'm only talking about any paved surface. Can be asphalt pavement, can be concrete, can even be brick stones or cobblestones. And the pavement surface conditions are dependent on a lot of stuff. Obviously, the weather plays a big role. We have precipitation. We have a lot of other. We can have evapor or condensation, like hoarfrost formation. A lot of processes are going on there that change the surface conditions. And traffic does also do its job. It can blow off materials, it can spray off sand, water and stuff like that, but it can also compact snow and it can polish the surface. And then it is the winter operations that try to counteract all these processes by mainly then plowing, scraping, applying chemicals or applying sand. That's basic, or any other abrasive material. Those are basically the four main things we can do with the pavement, which constitute of winter maintenance. So let's talk a little bit about some definitions. And if you like it or not, any road or any agency has a certain maintenance strategy when you design a winter maintenance setup. And the main one of the main strategies is what we call in Norway a bare pavement strategy. Now, this can be confusing because in the US, a lot of people use the word anti-icing strategy for this. But it boils down to the same thing, is that you try to aim, or you try to work to either keep the pavement free for snow and ice, or to restore it as quickly as possible. So you try to remove it as fast as possible. So key performance indicators for this strategy can be just simply the number of hours where snow and ice is on the pavement, or the bare pavement regain time. How long does it take after a snowfall or another event to get back to this bare pavement surface? The other strategy is what we call in Norway, at least, a winter road strategy. Now you allow snow and ice on the pavement for many days, weeks, maybe even months, but you still maintain that surface. So you allow the traffic to drive on the snow and ice, but you make sure that you have a sufficient friction level and also sufficient evenness. So here comes the scraping in to maintain evenness on those surfaces. Now, the reason why I don't like anti-icing as this word for the strategy is that it is also used for an operation. And if you talk about anti-icing, you always talk about de-icing. And to call this de-icing is not really true, because actually we don't necessarily want to de-ice. We just want to allow the traffic to drive on a snow and ice surface. So that's why we, at least in Norway, prefer to use terms bare pavement strategy, countering or opposing winter maintenance of winter road strategy. So, and on all these, in both strategies, you always need a plow. Basically, the plow is really the snow plow is really the workhorse for winter maintenance, as I see it. Huge amounts of material can be removed efficiently by a snow plow, much more than salt is by salt or any other de-icer can do. So let's dive a little bit into the fundamentals of plowing. A plow consists of different elements, and the biggest one is basically the mold board. That's the big curved shape what you see, and the mold board is typically made out of metal or some composites material, but mainly metal. Often there's placed a skirt in front of it, which basically often is kind of fabric. The main function is to prevent that snow blows over the plow, and starts to create visibility problems for the driver. The bottom of the plow, the part which is in contact with the pavement, is called the cutter edge. And the different type of cutter edges, the main function here is to pick up the snow and allow it to flow into the mold board. While driving, now the snow starts to accelerate while it is in the snow plow. And if you look from above, usually there is a certain angle perpendicular to the driving direction, which we call the angle of attack. And most plows you can vary this to some extent, which will change the way how the snow is cast out of the plow. Now, typically the cutter edge is not very much loaded. In most cases, the weight of the plow is actually partly relieved by some kind of system, either by supporting wheels on the back or by some levering system on the truck. So that means that the downforce or the vertical force on the cutter edge is not that much, typically 10 to 20 kilonewtons for a 2.5 meter wide plow. That means that it doesn't really wear so hard, and it basically, well, the plow doesn't really flow. There is some contact pressure, but it's not so much. That's different for an underbody scraper. Here you can put much more force on your blade. You typically use another type of cutter edge, and this is then intended to remove more compacted snow and is much more efficient to restore evenness in your compacted snow layer. While the plow is mainly made for removing the looser material. Okay. And then there are a bunch of cutter edges, or this is an element which has been rather developed. You can have rather standard steel, carbon steel plates which wear down, or you can have rather advanced systems of carbide steel composites and even carbide inserts placed in some kind of polypropylene or any other or a rubber type of material. Or you can actually have just composite materials. They use these at airports, at least in Norway, because the runway has some flushed lightings and a steel blade will damage those lightings. So they are more, they cause less damage to their infrastructure. In some plows, at least in Norway or in Hill Scandinavia, this is very popular, is on the back of the plow. So now we are on the back side. There is an extra element of rubber which you can push down on the road surface, and this is what we call slush elements. So if we go back to this, it will be located in this area here where you can see my point. And the function of this is that if there's any material, specifically slush, is difficult to remove in the plow, it's very, very, very heavy. So sometimes there will be some slush getting under the plow or is not getting caught by the plow, and that is then removed by this scraping blade of rubber. Now, the angle by which this cutter blade is placed is called the rake angle. And there are different definitions in different countries. Some people can call a 0 degree angle a vertical. Others call a 90 degree angle a vertical. So there are two definitions used both. So as soon as you talk about the rake angle, make sure that you know whether people talk about what is the vertical. And a plow needs to do a lot of things, but the main two key performances of a plow is the cast. It has to accelerate and cast the snow to the side, and how does it cast the snow is dependent on the plow's design. And the second one is the clearance performance. How much % of the snow in front of the plow is actually removed when the plow is driving over it, and how much % is slipping under. So the cast characteristics, they are heavily dependent on the plow design. On the left side, you see what we call diagonal plow. It's a very big plow, and they are designed to cast very far and very high. They're mainly used in rural areas and in mountainous areas where we have a lot of snow. And the reason why you want to cast far is that you place your snowbank far away from the road, so you can store a lot of snow before you get troubles that the snowbank gets too close to the road. But in an urban area, you typically don't want to cast so far, because often there is private area there's maybe a sidewalk, or there's something else there, or parked cars. So then you need a plow which is much less aggressive when it comes to the cast. And all these things are speed dependent. So the faster you drive, the further you throw your snow. When it comes to clearance performance, how good is the plow, how efficient is the plow in removing? How much percent of the snow is actually removed by the plow? This also depends on a lot of factors. The key factors are the driving speed. The faster you drive, typically the poorer becomes the clearance performance. The amount of rutting in the pavement has quite a bit of say. Unfortunately, in Norway, you have a lot of poor quality pavements with rather significant rutting, and that decreases the clearance performance. The type of snow, fluffy new snow, is much easier to plow away than heavy wet snow or slush. And as I touched in, the design of the plow also plays a part here. And finally, the plow adjustments. How is the plow? How aligned is the plow? How are the cutter edges? Are they worn down? Are they still straight? For plows with a load load relief system, how is that compared to, so how much downforce is actually on the plow? All those details can affect the clearing performance. There is some data available on the effective plow. This is a collection of studies done in Norway, where we measured the clearance performance by simply scraping with a vacuum cleaner and a brush the amount of snow before and after the plow. And what you see is that at 40 kilometers per hour, then you have a rather high clearance performance, up to 90–95%. But as you go higher in speed, basically all the plows will reduce their clearance efficiency. Now, typically there's something what we call cycle time. It's how long the plow takes to drive its route. And if it's snowing heavily, it's at least in most cases normal that the plow is just driving multiple times. And in that case, it's maybe not so important to have a very low plowing speed. But once the snowstorm is over, and you want to remove the last amount of snow before you are placing chemicals, for instance, then it's very important to keep your speed down so that you have maximum efficiency of clearance. By that you can save a lot of chemicals. I will come back to that later. So that was basically some of introduction on the plowing. Let's now talk about anti-icing and de-icing chemicals. Because anti-icing and de-icing is heavily discussed in the field, and there are different type of chemicals used. There are tons of brand names, but the majority of those products, they consist of either sodium chloride, calcium chloride, or magnesium chloride in different forms, or non-chloride alternatives such as formates and acetates. Again, there are many different types and brands, but these are the main type of chemicals that are used for winter maintenance. So let us talk a little bit when we talk about these chemicals in why are they applied, and now we are talking about operations. So for me, an operation is an event where the truck is actually driving out and we are spreading out chemicals. That is an operation, and in Norway we define now 3 types of operations. One is anti-icing, otherwise it's anti-compaction, and the last one is de-icing. And all of these operations are used in this bare pavement strategy. Anti-icing is what we call anti-icing in Norway, is only adding chemicals either to a wet road, which you're afraid of that is going to freeze, or when you expect hoarfrost formation. So you have a high humidity and a cold pavement, and you're afraid that water vapor directly turns into ice on the pavement. When it talks to salt or chemical applications before a snowstorm or in an early phase of the snowstorm, we call that anti-compaction. And the main purpose is not to melt all the snow. The main purpose is to prevent that the snow gets compacted into a hard layer. And the last operation is a de-icing operation. Now ice has been formed. You tried not to do that by your anti-icing or anti-compaction, but now slippery conditions, too slippery for what you want, have been occurred, and now you have to actively remove that ice by melting it away during de-icing. Now, de-icing can also be done in a winter road strategy, but that is only when you go from a cold period to a mild period and you want to make the transition to go shorter. Then you also use de-icing. Otherwise, you just typically do not use any chemicals. Okay, so now we have these three operations and the purpose why we use chemicals, and now we can dive into the fundamentals of this. How are chemicals actually working in an anti-icing operation? How are they working in an anti-compaction and in de-icing? So let's go. If you look at a pavement, you will see that a pavement is not flat. It has some certain roughness. You will see different stones, or either it is a concrete or an asphalt pavement. It has some roughness. And if you would take a magnifying glass and look at one of those tops or one of those hills, you will see that hill consists again of a lot of hills and valleys. So it has again a certain roughness. If you now look and zoom into even further into one of those tops and you take a microscope, you will again see a certain amount of roughness. So a pavement is a rough surface on different levels of magnification. And that roughness is very important for friction, because a rubber tire will just deform when it's pressed against this rough surface, and the rubber and pavements are gripping into each other, and now we can create friction, accelerate and brake. So if there's a layer of water on that pavement, that's typically not a problem. As long as not a large amount of water, so we can get hydroplaning, then typically this is easily handled by a vehicle. There's usually no problem. Problem comes when that water turns into ice. Now, we suddenly get a change, and the change that occurs is that in a liquid, as long as water is liquid, the molecules are not connected to each other. They can still freely move. But in solid, as soon as it freezes, they start to form bonds with each other, and each water molecule can make 4 bonds with its neighboring molecules. So I tend to illustrate this by the difference between having a bunch of guys standing on the dance floor when they are liquid, or when they are sitting in a bar drinking a beer. When they're at the bar, they are sitting in a locked position, connecting to the neighbors. They're still moving a little bit, but when they're on the dance floor, they're much more freely moving around. Now, and water has, or each those water molecules, they have a preferred state. The preferred state below 0 degrees Celsius or 32 Fahrenheit is to be solid. And as long as it's above, then they prefer to be liquid. And that balance, that can change. And it can change by dissolving something in that liquid. And dissolving something, it doesn't really matter what you dissolve in water. As long as you can dissolve something in water, you can make it more attractive for these molecules to be liquid, which basically prevents that even if it's 0 degrees Celsius, that there will be no molecule going over from the dance floor to the bar. And this effect is what we call freezing point depression. So we can push down that equilibrium temperature by dissolving something in the liquid. And I used to say that it's just more attractive if you add a little bit of woman to the dance floor. So if you look upon that, then you can see you could envision that adding chemicals to your wet road, it's basically add some women to the dance floor, making it more attractive to be there. Now, a chemist would call that would say that this is what we lower the chemical potential of the solution. For me, that's too difficult to understand, so I just like to envision it as being more attractive to be there. Now the question comes, how much chemical do I need? If I know the amount of water and I know the temperature which I expect, then I could basically say, okay, give me the number, how much chemical do I need? And basically that number is given in the phase diagram. The phase diagram is a diagram which shows on the x-axis the concentration of your chemical, in this case sodium chloride. So 20% means that 20% by weight on the road is sodium chloride and 80% is water. And now you have the freezing temperature, or you have the temperature on the y-axis. And this curve you see here is called the freezing curve, the freezing point. So 10% chemical in my solution gives me a freezing point of -6 degrees Celsius. Now, don't make that mistake that if you go to this point, that suddenly the freezing point goes straight up again. This is something, it's a very persistent error in the field, but the freezing curve is not going down and then up again. The freezing curve of water is just going down, 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 down to a certain point, and then it stays flat. It stays at, in this case, -21.1. Because this curve is another curve. It's simply the solubility of the salt. You cannot dissolve endless amounts of sodium chloride in water. If you take 30% of salt and you put it in water, only 20-something percent, 20 at -21, 23% of the salt will be in solution. Any other salt cannot go into solution, and if it cannot go into solution, it cannot make it more attractive to be there on the dance floor, so it will just stay exactly the same. Your freezing temperature keeps it at -21 degrees Celsius. So now you may think that, okay, then I just have this curve and I always have to make sure that I stay above this curve. So I want to salt so much that if I know the amount of water that's on my road, then I want to make sure that I'm always above the curve. So I'm in this area here and I'm sure that there's no ice on my pavement. That's fine, you could do that. But actually what we found in different field studies, both in Sweden or in Norway and in Finland, was that if you now look at the pavements and you measure the temperature of the pavement and the water film and the concentration, so all of these were wet roads, we see a lot of dots which are far below this curve. And yet all the black dots or the solid dots, the road surface conditions were not bad at all. The traffic went as normal, it was like nothing was happening, it was not slippery, yet there was much less salt available on the pavement as what you would expect from the freezing curve. And why is that? Why can we have apparently a sufficient result, not slippery, it was still okay, while we do not have so much salt to keep the water at its freezing point? Now, the reason to do this, or the reason for this, is that we have to go a little bit deeper into what happens when a water freezes. If water freezes, if you have just pure water, it will start at, the freezing process starts at 0 degrees Celsius or 32 Fahrenheit, and all the water can freeze at the same temperature. So what you see here on the left side is a droplet of water that has been frozen in the microscope, and we're looking just at the edge here. You see the edge of the droplet. So this is only 0.1 millimeter, and you can see that you can see the grain boundaries between the crystals. So we have different crystals in the ice, but they are all firmly attached to each other. But if we add a little bit of salt to that water and we let the water freeze, we see something completely different. Now we see parts of ice, what you see here, which is the darker areas here, but you also see some lighter areas, and that is still unfrozen water. So even though the temperature is below the freezing point, we still have some unfrozen water in them. Why is that? Now, let's say that we have a solution with some concentration of a chemical, and let's say that the freezing point is -4 degrees Celsius. If the freezing starts, only the water molecules will go to the bar and they will make bonds. So all these water molecules, they are going to solidify, but all the salt is pressed into a smaller volume. And at some certain point, since now the concentration is getting higher, because more water is removed from this area, but the same amount of salt is there, the concentration goes up. And as the concentration goes up, your freezing point goes down again, as we've seen in the phase diagram. So at some point, the freezing will just stop. The concentration is so high that as long as we have some ice on the road, but there still is some unfrozen fraction of saline water on the road, and this sits then as pockets inside the ice, and that makes the ice much weaker. So if this ice has enough pockets in there, it will be so weak that it cannot sustain the traffic. It will just break down in small pieces while your traffic goes over it. So we've done some studies there, and we were looking at, okay, if we change this frozen fraction, we can calculate how much solution, how much of the total water is frozen and how much of the water molecules is ice. Basically, we found that as long as there's more than 25% unfrozen water, this unfrozen fraction is at least 25%, then the ice is so weak that some mechanical action will just remove it, and the tire can go back into the roughness of the surface structure. So that's basically the main mechanisms of anti-icing. First of all, it depresses the freezing point, and secondly, if the water freezes, it will weaken the ice that forms. And that's true also for hoarfrost. So the main physics behind anti-icing is both valid for freezing a wet pavement or for hoarfrost. Again, I will talk about snow, snowfall, and snowstorms later. Now, let's first, before I go into snowfalls, let's first talk about de-icing, because we need to understand some concepts of de-icing before we start to talk about anti-compaction. So now we have a road. Our aim was to keep it bare. We, for some reason, did not manage, and we have to do something. We have to treat this pavement, and we have to melt away this ice and try to restore the pavement in our desired state. So now we are going into de-icing. And again, how does it work? What are the fundamentals? Well, we have to go back to this system of water and this equilibrium. And we have discussed already, if we lower the freezing point, we make this solution more attractive, and we prevent that the water freezes. But in the meantime, since we have made this so much more attractive, it is still possible for an ice molecule to go over to the dance floor. So this molecule, it will just try. We kind of seduce this molecule to go from the ice, leave his neighbors, leave the beers, and rather go and be happy on the dance floor. So as long as the freezing point of this solution is lower than the temperature of the ice, people or molecules will go over from the ice to the solution. So we not only lower the freezing point, we can also actually melt at lower temperatures. As long as ice can melt towards a solution, we can melt it at lower temperatures than 0 degrees Celsius. But the main physics is basically we are seducing this molecule to go, and we prevent that any other molecule falls back into this lattice of ice. So it is the solution that does the job. But there is a little problem here, because this molecule, it will go over. This was a highly concentrated solution, a lot of salt molecules compared to the number of water molecules. So it has a very low freezing point. But this one goes over, and the next one comes, and the next one comes. And by the millions, these molecules will go over from a solid state to a liquid state. And that dilutes this solution. So as the melting process goes on, we are more and more diluting the de-icer. And at some point, it is equally interesting for a molecule to be here than to be there, and now the melting reaction stops. Now the temperature of now the freezing point has been climbing up due to the dilution up to the temperature of the ice. And at that point, we basically cannot melt anymore. And if you use a liquid, if you use a brine, this goes very, very quickly. Because in a brine, if you add a liquid already pre-dissolved de-icer on the road, you have very, very little melting capacity. Because as soon as this happens, you will start to dilute, and it will very quickly, the reaction stops. So therefore, it is beneficial to have some kind of storage of chemical localized available. So, and that can be a particle. So a solid particle can be viewed as a kind of reservoir of salt molecules that can go into solution as the melting process is going on. So now we have two competing mechanisms. One is the dilution, or the melting reaction, which dilutes the solution, and one is then the grains of salt that can go into solution that try to keep up the concentration. And by doing so, we keep up this driving force, and we keep it so attractive to be here. And now the reaction can go much further. And we can actually calculate this, and we can calculate it in what we call the melting capacity. The melting capacity says something on how much ice I can melt with a given amount of de-icer, typically in grams per grams or pounds per pounds. So for a solid sodium chloride at -5 degrees Celsius, for 1 gram of salt can melt approximately 12 grams of ice. But if we take the same gram of solution of brine, we can only get 2 or 3 grams ice melted. The reason is that we have by making a brine of 23%, if you add 1 gram to the road, only 23% of that gram is actually salt. The rest is just water. So that reduces your melting capacity severely. And all that water that you used at the garage to make your brine, if you make your brine yourself, all that water could have come from the ice. So that's also a kind of melting capacity which you cannot have because you have added already the water to the de-icer. So summing up, it is favorable, or it is much easier to succeed or to get success with a de-icing operation if you use a granulate. But if you need to de-ice at very low temperatures, or I didn't say, but what you see in this curve as well is that as it gets colder and colder, your melting capacity goes drastically down. So it is not favorable to de-ice at very low temperatures. So if it gets very, very cold, you may, or some agencies or some truck drivers have already experienced that adding chemicals doesn't really work, and I rather need to wait on, maybe you use some gritting instead or some sanding, but wait for warmer temperatures to do this de-icing operations. But what you could do is pre-wet your grain, because if you go back to this system here, if we do not pre-wet and we have just a grain of salt laying on top of a piece of ice, there is no solution. So there is no favorable place for these molecules to go into, and that there's no dance floor. It's just a bunch of guys sitting drinking beer and a bunch of women on the other end drinking red wine, and nobody is actually trying to come on the dance floor. So pre-wetting, if you add some liquid to your grain, it will kind of kickstart the reaction and make it more easy for the water molecules which are sitting in the ice here to actually melt and go into solution. So that was de-icing. Now, anti-compaction, and this is, I said it in the introduction already, this is a word not much used in the industry, and in Norway we are using it for now many years, and I'm sure that people have done anti-compaction, but they have called it just anti-icing, and we have separated those two words. So the real aim of adding chemicals prior to a snowstorm or during a snowstorm is to keep the snow plowable. It is not to melt all the snow. If you do that, you will need much more salt or chemical than you typically would use. So I think that's the biggest misconception in winter maintenance, at least by the general public, is that the purpose of the chemical application is to melt all the snow away. It's mainly the function to prevent that snow gets compacted and forms a very hard compacted layer, which then gradually turns into ice. So I like this word, keeping the snow plowable. And how does it work? Well, let's take a situation where we don't do anything. We just start with a snowfall. snowfall, we get a lot of snow crystals falling on our road, and traffic directly starts to compress it. We bring the snow crystals closer to each other, and it's very similar as making a snowball. You increase the density, and then something happens in the snow. Because if you have two different pieces of ice, which snow consists of, then two loose pieces of ice, if you have a very, very sharp curvature, like here in the contact area, it's very favorable for molecules to be here and actually start to make bondings between those two grains. So two initially loose grains start to get bonded, and this is a process which we call sintering. And that's why you can make a snowball. And if you do that on a road and you plow this, you get a compacted snow surface. And again, in a winter road strategy, this is what you want. But if you're running in a bare pavement strategy, this is what you don't want, because this can turn it slowly into ice and starts to become very difficult to remove. So the key is to add chemicals in this early stage, either by pre-treating before the snowfall comes, or as soon as the snowfall starts to fall, we start to add chemicals already here in the system. And what it does is that it basically prevents this sintering process. By having a solution there, it prevents that these water molecules can start make bondings between the snow crystals. And so the real mechanism, or at least the mechanism of how this works in practice, as we view it, is that we apply these chemicals in an early stage. And indeed, some of the snow will melt. And as it melts, it dilutes the chemical. And you can melt until you have reached your melting capacity of your de-icer. So you could actually theoretically calculate how much snow I can actually melt on my pavement. And at that point, still there's no grain of snow on my pavement, but my pavement is wet by this diluted de-icer. And that diluted de-icer, that is really the key of how to get these bonds, how to prevent this bond formation. And this is a part that we have been doing quite some bit of research on. And the first thing what we was interested in is, okay, how much % of diluted solution do I need to add to the snow to change its strength? And what we see is that just 10 weight% of solution, so there's 10 weight% of diluted solution, gives a big reduction in strength of the snow. This was an experiment which we did in the lab, where we were pushing a little pin into compacted snow, and we were measuring the force it needed to press this pin into the snow. So that's what we call snow hardness. And just adding 10% of diluted solution into the snow reduced this hardness by around 60%. We continued that research by making now, this is our latest work, by adding these diluted solutions on with different concentrations or different contents by 0, 5%, 10%, 20%, and 40%. And we were simulating the worst case of compaction, which is basically snowfall very close to 0 degrees Celsius, and you have got already traffic jams. So now that the traffic is very slowly driving, around 10, 20 kilometers per hour, and really compressing the snow. So there's a lot of time to compress the snow. And in that cases, we basically found that 10 weight% starts to get enough to get your pavement already partially bare if only 20 vehicles pass over this. So this is typically on a high traffic road, it's very quickly done. So you don't need much, and if you use a scraping blade, 5% is even enough to weaken the snow sufficiently, so a snow plow can remove this. Now, hopefully, these numbers can be used in the future by some decision support models, so we can. That's my dream actually, to work towards decision support models for that can actually predict how much chemical I need to add on the road to get sufficient anti-compaction. So the last part is the sanding, and I'm running almost over, or time flies. But the last part of the paper or the chapter is dealing about sanding, and sanding is mainly done in this winter road strategy. And to understand how sanding works, we have to understand a bit more about how friction is created between a tire and a pavement. And I talked already about this importance of roughness. As long as we can give roughness to the tires will deform, and then we will get interlocking between the rubber and the pavement, and then we get a good friction. So one way of viewing sanding is that you actually add texture or you add roughness to the surface. I will jump over this one. But typically, if it starts to snow, and specifically if it starts to ice, we start to lose our roughness, or the roughness gets covered. And if there's still some roughness in the snow, we get some friction. If we don't have any roughness in the snow, then we get very little friction. So placing sand particles there is basically adding an extra medium, hard particles, which the main function is to concentrate the load into small areas, localized areas, so the sand particle can penetrate into the snow layer. And since there's quite a good roughness or grip between the sand particle and the rubber, typically those particles tend to be dragged with the rubber if the rubber starts to slide, and then the particle starts to slide over the snow and starts to plow into the snow or ice layer. And that gives friction. That gives better friction than if there was a direct contact between the rubber and the snow. So some countries still allow studded tires, and sanding and studded tires, the physics is pretty much the same. We have a localized hard particle under the tire that can scrape and plow into the snow layer. But if you do that, you can actually see the effect of it by scratch marks. This is a picture taken on a sanded runway in the zone where the tires break, and you can see all these thin stripes, which is basically scratch marks of these sand particles scraping the ice, and by that way trying to get more friction. So that's the main function of it. But if you sand smartly, if you add sand early enough and the snow is still white, you may have a chance that some of the particles can actually get embedded in the snow layer, and the snow layer gradually turns into ice. And that's the case what you show here. So at this airport here, they add structurally sanding in an early phase, and the sand particles get basically embedded into the snow and ice layer. They run this airport throughout the winter on the surface, but because we have so many sand particles on the surface, you get almost a sandpaper effect on this, and then you can get very, very high friction. So that was basically the main ways how sanding is working. Now, there are a lot of disadvantages by sanding, and particularly if you have high speeds or high traffic volumes and you add particles on a pavement or on snow and ice, they tend to just blow away, and the effect is very short lasting. So typically the high speed above 60, 70, 80, or 80, 100 kilometers an hour is typically not very useful by sanding and gritting. Then you typically tend to go to this bare road strategy. But on rural roads and in colder climates, it is still a useful way of actually, and maybe actually a better way to maintain your road surfaces. So that was basically my talk, and I thought I will close this by summing up what I've been talking about. We talked about winter maintenance. I went into these two different types of strategies to maintain the surface. We started by plowing, which was used in both strategies. We talked a bit about the different elements of the plow and the important parameters, which was the cast and the clearance performance. We then went into anti-icing, which I define as the application of chemicals for wet pavement or against hoarfrost, where the main mechanisms is both freezing point depression and weakening the ice if any ice would form. Then we talked about anti-compaction, which is basically keeping the snow plowable. And we melt some snow that dilutes the de-icer, and it's the diluted de-icer that prevents the bonding and keeps the snow plowable. And then we went into de-icing, which is part of a bare pavement strategy, but also can be done in a winter road strategy when you want to convert or at the end of the season. And here it is mainly that the solution of a chemical in water that melts the ice, that's what it makes it attractive. But it is important to have a grain which can be viewed as a storage of chemical that can go and keep up your concentration. Any chemical has a certain melting capacity, and the melting capacity of a solid de-icer is much higher than a liquid de-icer. The last part of it was a high temperature dependence. So it is easier to succeed your de-icing operations if you're close to the melting point rather than if you're very far away from the melting point. And finally, we talked about sanding. Very briefly, we discussed some friction mechanisms. We discussed the importance of roughness, or viewing sanding as a way to add roughness to the surface, and the difference between loose particles that scratch the snow contra big particles that get fixed and embedded in the snow and ice layer that can create a kind of sandpaper effect. So I hope that this was understandable and maybe to some valuable for a newcomer, a student, or a professional even. So thank you very much for your attention. Are there any questions? Everything was very clear. Okay then.
Thank you, Alex.
Thank you.
Yes, thank you, Alex. I'd like to let everyone know that this presentation was eligible for professional development hours, and so anyone can contact me and for a certificate that attests that. And to remind everyone that our next seminar in the series will be performance measures for sustainable winter road maintenance operations, which will be on Monday, June 17th.
Okay, thank you very much and have a nice day.